Welcome back. We've talked about binary trees, binary search trees, and then we learned about how to balance those trees and some of the time complexities involved with a BST. And I want to talk to you about two other common type of trees. One is a heap, and the other one is a tree or tree. In this video, let's get talking about heap. Now, when it comes to heap, we're most likely going to talk about binary heaps. Just like we had with binary trees, that means there's only going to be two children to a node. Now, why are these useful and how are they different from binary trees? Let's go have a look. A binary tree, every child belongs to a parent node that has a greater priority or value. If you look over here, every child, that is 72 and 33, is lower than 101. 72 is higher than 2 and 45, and 33 is higher than 5 and 1. This is actually called a max heap. There's also something called a min heap, which is the exact opposite, where the root node is the smallest. Now, this value can be anything you want. It can be a person's name, it can be a number, it can really be anything because it's a node. But as you can see, all we're dealing with is that in a binary heap, every node on the top level has a greater value than every node on the next level down. And a heap can be used in any algorithm where ordering is important. And as we're going to discuss, it's commonly used when it comes to priority queues. Now, with arrays, we had random access. It allowed us to randomly access any element within them using an index. In a linked list, we can change things dynamically, unlike an array, but finding something within them is O of n, linear time, because we had to go through the linked list. Heaps are a little bit different. You can't do O of 1 random access like we did with arrays or hash tables. As we know about trees, we have to do some sort of traversals. Now, compared to a binary search tree, we see that, well, lookup is O of n. It's not O of log n, because it's less ordered than a binary search tree, right? A binary search tree actually had meaning between left and right child. The left was always less than the right. In a binary heap, that doesn't matter. Left and right can be any value as long as it's less than the top value. So if we're looking for, let's say, 1, we have to check the parent node. Then we have to check, because 101 or because 1 is less than 101, we have to check both nodes underneath it. And then because 1 is less than 72 and 33, we have to once again check every single node. And looking for 1 becomes O of log n. So it pretty much turned into searching through a linked list or iterating through an array. So why would we ever want to use a binary heap? Well, it turns out that binary heaps are really, really great at doing comparative operations. Just like saying, I want people that have a value over 33. Because in that case, we can just grab these items quite easily instead of going all the way down through the nodes. Heaps are actually used a lot in data storage, priority queues, sorting algorithms. So let's have a look at how a binary heap is implemented visually. We have a binary heap here using Visual Go. And if we wanted to add, let's say insert 26, we hit go. All right, that was really fast. But what if we wanted to insert, let's say 51? If I insert 51, I had to do a bit of a switch. You see, heaps add value on the tree in order from left to right, and then bubbles up if it's not in the same order or the priority order that it wants, kind of like we did here. So if I add, let's say 70, or you know what, let's add 100. What do you think will happen? Well, if I hit go, you'll see I add 100 and then it bubbles up. So as you can see, inserts, although it looks fast, can still take log n. And this is the same case with deletes as well. It's O of log n. Now, in order to truly understand why we need something like a binary heap, why they're so useful, how they're different from binary search tree, we need to talk about priority queues. So let's talk about priority queues.